So, hi and welcome again from the other side, speaker side this time. And I'm going to talk about what you can do when it's already too late. You got your segfault, and now I will structure my talk into two parts, two bigger parts. One part is more like a background, more like the traditional ways of looking into crash dumps. This will include the situations that is a little bit different in embedded, working with core dumps, signal handlers, special watchdogs you can have or the system has for you. And in a second part, I will show you a specific serving suggestion combining Yocto and Google Breakpad and Sentry to have a nice integrated system that allows you to get an email every time a crash happened, maybe even at the users in production. And in the end, I will also talk about this a bit, like the legal aspects of it. Like every talk, the scope of this talk is limited. I will not cover all crashes possible. I will only talk about the crashes that happen in C and C++ specifically. I will concentrate on embedded Linux. What I'm going to show you might apply for Windows or QNX as well, but I cannot really promise you that. And I'm also going to talk about crashes induced from the outside of a process and the inside of the process, like a classical segfault. My assumptions are that the operating system must be still fully functional and we get no kernel panics, so we are still in a good software state to reason about the software. And also the software developers' assumption number one still holds: hardware just works. With that said, let me start with the background. Embrace the fail. I mean, we all have seen crashes. We all have seen calls from our customers saying, "Hey, Christoph, what's going on? My program crashed." And everything I can say, like, "What did you do?" And they would say, "I cannot really remember," or "I don't know what happened, but it somehow hangs now." And for all of this, we have crash dumps. And crash dumps can help us find out more about our errors or the mistakes we did in order to improve the software quality in the end. So crashes are different in development and in production. We have kind of these two situations, right? In development, we are usually well off with lots of symbols. We have a GDB debugger on our target, maybe a GDB server on our target. I will go into this in a bit. We can have full-size dumps, so we can dump everything of our application stack, full memory, maybe even the data the application worked with. And we have eval boards where we have maybe more storage on it, and we can like test even more. On the other hand, like a bit of a downside of the development situation is that we have a small testing surface. Only the few developers, maybe some testers, are really out there and looking for those errors that we want to find. In production, however, everything is a bit reversed. We have slim images, so we cannot have all tools on our images. We oftentimes also have only slim dumps, like slim crash reports, where we only have the stack and cannot read all the data of the process that crashed. We have maybe reduced bandwidth, where uploading the data is complicated because the device might be remote. And also in production, we have limited hardware because we now have the big numbers, the thousands, the 10,000s, or the millions, where every cent counts. And this cent needs to be saved mainly on storage. And this is where it's getting complicated to record proper crash dumps. On the other hand, we have a large testing surface. So we have many users out there. We have more testers. We have more versions out there to crash and more to learn about our softwares and the problems inside there. But basically, it boils down to storage versus non-storage. To talk about crash dumps, we also need to talk about having symbols inside our programs. Symbols are needed for multiple things when we want to analyze our crash dumps. So the first and most important ones is that we have only addresses in the crash dumps, and we need to make them readable and understandable for humans because we usually cannot really understand the binary dumps that are coming to us in these crash dumps. There's a second thing that is really important. It's called stack unwinding. And sometimes your program or your crash analysis is not really able to find out the stack of the program that crashed. And it needs symbols in order to really reconstruct the stack, so the order of functions that was executed and which led to this crash in the end. And also something that is good for us developers, we want to infer line numbers. We want to know, okay, it crashed in main.cpp in line 316. You will get all these symbols, you probably know this, with -g, just having symbols inside there. But don't be fooled, it's not a debug build when you put -g. You can also have optimizations and symbols, -g and -02, which I call a profile build. And these are independent of this optimization. So you always can have both. But symbols are huge. And sometimes, as I said, we don't have lots of space on our devices. And it's hard to hard to get them all on the devices. Here on the right, I made some images. First, you can build your app with symbols. But then if you want to save on space, you can strip them out. And there's also a process called symbol unstripping, where you can recombine the app and the symbols to, again, have an app with symbols that can maybe be analyzed better in the end. Also, you can use the symbols and the memory dump, as I said before, to do this stack unwinding to get a real stack trace for your problem. This is just a short overview. Code is embedded in many execution contexts. And in all of these contexts, we kind of have a trampoline, or we kind of have a net that can catch us. So we can have crash handlers or ways to report on crashes on all of these levels. So inside the frameworks, maybe Qt, inside the C runtime, signal handlers, then processes, and also app managers like systemd, systemv, the operating system itself, and the hardware, or even hardware components that are outside the hardware, where we send a heartbeat to, and that find out that something is wrong and can make us crash, and such that we report our crashes. Let me come to the most basic crash reporting system, or which exists on Linux, which is core dumps. I do not know if you know, but the word core does not stand for the core of your program or something like that, but it stands for the core memory, that is these ferrite cores that existed before we had real RAM and a real disk. And this is a funny project by Jussi Kilpilainen, which is an Arduino module where you can actually have those old core ferrite cores, and dumping a core or having a core dump just means writing all your memory, right? Because back in the days, cores was all you had, and dumping your cores means, okay, dumping your memory. When we look into core dumps a bit more in detail, we will see that core dumps are actually an ELF file, so a Linux executable and linkable file. And so, it's like an exe, yeah, like an executable binary for Linux. And as such, it has regular ELF headers. There's only one thing that's different. It says, I am now a core and I'm not an executable program. But for the rest, it looks pretty similar to a normal program. So you have your virtual memory addresses mapped to the dumped memory below here, which is following. You have some nodes, which core dump calls nodes. There's nothing like user nodes or something like that. This is actually registers of threads, stuff that wasn't thought of in the beginning. And in this node, extra information is stored. And then we have process informations like the user ID who ran this process, or the group ID, or the state the process was in when there was a dump. Also, we have information for all of the threads and all of the mapped files. That also includes the libraries, for example, Qt, that was mapped during the execution of the program. Okay, what do I need to have in order to have core dumps? Oftentimes in your Linux distribution on your desktop, that is super clear. You always can have core dumps. You just get segmentation fault, core dumped, nice. But in some distributions, or when you build your own distributions, you need to keep in mind that you enable the config core dump when you're compiling the kernel. Also, the executable, which should be dumped, must be readable. And this is a security feature because cores actually reveal your secrets. And there's the option in Linux that you execute a program that is not readable, but executable. And then creating a core dump from this would give away all the information of the program. For this reason, it is not allowed to have a core dump of a non-readable program. Also, the processes must have permission to write the core, which is also the way to turn it on. I'll show you in a second. And on embedded, we again have the problem. You need enough space to store it, and you need enough bandwidth to transfer it, or you need an internet connection or some kind of connection to transfer it. Okay, I said it's only generating a core dump for you when you have when it's able to write all the core dumps. And there's actually a limit for that called ulimit, a different section in ulimit called core file size, which you need to set to a value bigger than 1 in order to write a real core dump. Here I did ulimit -a, and by standard on embedded devices, you usually have it turned off. Just check with ulimit -a and find out if it's 0. If it's 0, no core dumps can be written. Then in a second step, I set it to unlimited. And after I set it to unlimited, I can also query the features with -a, give me everything again. And now it tells me, okay, you have unlimited permission to write core dump bytes. Okay. The type of, or kind of the name of the core file, or the path where you can find it, you can determine yourself. In this path, you see on top here in the proc file system. And it's basically a file where you just put a path with some placeholders, and you can see all those placeholders here, like a process ID or user ID or group ID, which can then appear in your core file if you ever want to upload a core file. In the case of development, I would argue if you have enough storage, you should have a GDB on your target. So if you don't have a way to store a core dump, which you then enable on your target, you can get a bit creative. You can say, okay, maybe I have a USB flash drive that I can put here. Or maybe I can mount a network file system or something like that. Remember, if it's crashing and if it's writing the core dump, you probably don't need to be fast anymore. You can also just like take your time and write the core dump. It's better to have the information than to leave it out. And also, if you get a crash producing a core dump, I said you can unstrip binaries and symbols back together into your binaries. And this will make them bigger, but you will be able to understand more of your GDB session when analyzing this core dump then on your target. And you can repeat that for all the relevant libraries, like find out what you need. And if you already got all your information, then fine. You don't need to like put in all the libraries that you have. Usually some are enough to find out the proper stack and find out what's wrong. Yes, it's tedious to get them in one by one. But if you need the heap information, so if you need information on like objects stored on the heap, or for example, from map files or something like that, then I would suggest you to do core analysis on the target. If no heap is needed, there are always better ways, and I will show you in a second more better ways. There's also a way of transferring the core dump first, and then to kind of analyze the core dump on your desktop system, on your host system. For this, you will need a cross GDB, so a GDB that is targeted towards your target's architecture, let's say ARM, but is running on your desktop. You will also need the exact same executable that crashed most of the times with symbols. Then again, symbols for all the libraries. The core file you need to transfer over. And optionally, if you want to look into your operating system's internals, you also want to get the symbols for the kernel, which are accessible for root in proc k-alsims. And then again, carefully feed SDK paths or libraries or SOLib search paths or symbols into your GDB, and see and rinse and repeat, see what happens, and see whether you get a proper stack trace. So here, down here, I wrote, okay, you can tell GDB, my sysroute is here, maybe an OPT SDK, or my SOLib search path, there's extra libs, these are here. And GDB is then able to find symbols or pick the libraries with the symbols so it can operate better and actually give you a better core dump. Okay. There's also a hybrid approach where you have a GDB server on your target running your executable. You already know it crashes, you want to rerun it. And then you can use it cross GDB on your host system and can have all the symbols and library symbols on your host system where you have enough of storage, and then do the analysis on your host while connected to the running executable or like executable in analysis with a GDB server on the target, which is actually really nice. And I do oftentimes when I don't have the option to store lots of data on the target. There's some nice features about core dumps that I didn't know when I started preparing for this presentation. You can actually advise, so tell the Linux operating system that certain pages should be excluded from a core dump. And you will need to pass the do not dump or advise don't dump flag to certain pages. And with this, you're then able to exclude this. Just imagine you have a big video file or something like that in your application. You don't want to have that every time in your core files. You can also pipe core dumps to standard in of another process. Maybe you want to send it over the network, or maybe you want to post-process it with some other process. And this is actually what core dump control does on systemd. It's just putting a pipe in this core pattern in the proc file system. And when you have a pipe, you can just have an executable after that. And one thing that is also surprising for me, and I didn't know before, there's a program called gcore, which is able to get a core of a running program, and the program will survive this procedure. And you can just have many cores, how many cores as you want, of your running application, which is maybe nice when you have an infinite loop or something like that. Okay. I told you before, there's also a way to get nice stack traces more easily than having full core dumps. And one library to do that, which I really like, is backwards CPP. It's by François-Xavier Bourlet, or Bombela. And the pitch goes as following. Are you tired of just seeing segmentation fault, core dumped, and nothing more? Well, then try backwards CPP, which you can see here. It prints on crash a really nice stack trace of your program at the point where it crashed. And it does so, as you can see here, with some context for all of the stack frames that you want to analyze. So here is the top stack frame where it happened. Here is a kind of a address 42 where I just wanted to write a 42. And turns out that produces a seg fault. It's telling me this. But I can see, okay, this is happening in this badass function, which was called here in this stack frame above, which was called from this stack frame above. And I can maybe even see all the information, like the surroundings of this. And this you can just compile into your application. And every time it crashes, it produces you this nice output. How nice is this? So here's a bit more information. Include only a header and one line of initialization, and you're done. Well, you're not really done. You might need add some unwinding libraries, but you will find out in backwards CPP's page on GitHub, for example. And you want to have them for your sysroot, obviously. Most of the time, lib unwind and the libs to look into ELF files. Also, symbols are necessary to do a proper backtrace in this way with -g. So your binaries will get a little bit bigger. And but then it does the stack unwinding and the signal handlers for you. And if you want to have this nice source code, it also requires access to the source code to print it. Yeah, you can decide if you want that. And it is really versatile, and you can just customize it further. And again, I can only recommend this for development. The sanitizers, if you have them enabled, can help you as well. Here's just an output of the sanitizers. I had the address sanitizer on, and I did a seg fault here. And this time, the top frame is on top. So I was crashing in this function, which I know. But down here, I can see, okay, I was coming from the QML, there was some problems in Qt, and I ended up in the functions which I really know well, and I know, okay, there was a problem here. And I cleaned it up a bit for you because it was way too large for the slide, but here was also information about the line of code that actually crashed. So I found the error really quickly just by having address sanitizers enabled in this case. Sometimes you have no symbols, sometimes unwinding fails, so you don't get a proper stack, or GDB just says corrupt stack, cannot help you anymore. There's still one thing you can resort to, a thing which I call desperate stack reading. And this is really small maybe, but I will explain what it does. So it's basically only printing the raw stack memory, garnished with some symbols that you told GDB to put to them. And this is something that is really rough and need to be taken with teaspoons full of salt, but sometimes it still helps you when you get a backtrace, but nothing more than that, or a core file, but nothing more than that. So what I did here is I set the ASM demangling to on, and then I just printed 300 bytes down the stack pointer. And yeah, with this, I just get some function names, which are maybe true, maybe they are also data, I don't really know. And at some point, there's also my main, and I might even read below the stack, but just for starters. And if I have nothing more, it's the last way I can resort to when I have a crash. Okay, but what to do when it's already too late? Is there still something I can do, or am I just out of options when I already received a seg fault? It's not true. Signal handlers can act and help you when it's already too late. So all signal handlers can be registered, and they are just normal functions. Not really, I will come to this in a second. But they are registered, for example, in your main with the C++ way with standard signal. And here in this case, in line 11, I register it to the SIG, which is the seg fault signal. And then every time I get a seg fault, this code will be executed. For the POSIX API, there's also SIG action, which is more versatile and allows you to do way more and get more information when you get a signal. Here you have to go the C way and have a struct, which is a SIG action, and set the handler on it. So basically, I set it here and then also register for seg fault and so on. But this struct will then have more information. Like, for example, I put here on the right, the SIG info type, where you can also find out the PID or the UID, like the sender info. If someone else sent you a signal, like a kill signal or something like that, you can find out who was it, who was killing me when I was dying. And then you can still react on your handler to that, or maybe distinguish and do different handlers for different processes that tell you those signal, those kill signal, or those seg fault signals or abort signals. Here's how a signal handler can look like, and I don't want you to look at the code. It's just an overall, just an impression. There's lots of C code inside here, and I will explain why in a second. A thing that we can still do here is to fork. You see that there's a fork here, so I can spawn subprocesses, and I can actually run subprocesses here, which is really neat. Yes, this is a special crash handler, which I use in my second example, but just to show you how it could look like. You can do lots of stuff. But you cannot do everything in a signal handler. For example, heap allocations, and mainly heap allocations, are forbidden because they are not asynchronously safe anymore. You do not have a real stack anymore. You're operating on unsafe territory here. And it's only permitted to execute safe operations. And again, that is basically everything that does not use malloc and free and goes to the heap, because that is actually not async safe. If you want to find out what you can do and what is allowed to safely be executed in a signal handler, then go to the man page for signal safety for it, and you will get a long list of everything that works. And that is only C code. For C++ code, you would need to know whether your code allocates or not in order to find out if it's safe. Be hyper careful of crashes inside crashes. You can still act in your crash handlers, but if you crash again, for example, with the same signals, you can get in an infinite loop that is hard to break, or you just spam some crash reporters or something like that. You have been warned, don't do it, be really careful there. However, there's things allowed in the signal handler, and you saw it already in my example. You can start new processes, which I find amazing because I can do everything I cannot do in the signal handler then in this new process, right? Obviously, you can read your own heap memory that's needed to dump. And also you can send signals to self. Well, you can always send signals to self and raise a certain signal like segfault and so on. Maybe not in a signal handler, I put it here, but like in general, you can send signals to yourself, but in signal handlers, I wouldn't do it. The most important feature for embedded, I think, is to reinstate safety on your embedded device. First, I only talked about, okay, we want to find out what went wrong, but maybe your device is in an unsafe state. Maybe you have a heating or a pump running, or some water is running over and spilling everywhere because your pump is not in a good state anymore, something like that. And in signal handlers, you can also reinstate safety, put everything to safe mode again for your embedded device, and then maybe the user can restart the device and start all over again. There's one cool thing that I really like. It's not really super safe as a signal handler, but I like to put it in signal handlers anyways. From KDAP on GitHub, there's the KD toolbox, and you can check out the QML stack trace dumper to also get a stack trace not only of your C++ context, but also of the QML context. So all the functions that were running currently in QML when the crash happened, maybe you find some more information about your crash there. So check it out. It's really worth it. Okay, then there's another process that might help you analyzing crashes or different kind of problems, which are infinite loops. It really makes sense to have watchdogs either in hardware or as processes around your main application out of the main execution context to check for infinite loops. So the idea is that your application periodically, maybe not in that infinite loop, but sometimes sends an update to this watchdog saying, I'm still alive, I'm still doing well. But when your application runs into a tight loop, reading a file over and over and over again, it will forget about sending the heartbeat to the watchdog, and the watchdog will then be able to make your system crash or your application crash. And with this crash information, you then in turn can find out where you were in the stack trace, in that infinite loop, when you analyze the stack trace or crash dump later. Yeah. So that's actually really nice. And that's something you can think about as I'm not really crashing, I'm actually still alive, but I'm not doing what I'm supposed to do. And you can still analyze upon this. Really nice. There's one external process that is watching you all the time, which is the killer, the Linux out-of-memory killer. And yeah, that is the most famous external source of an unwanted termination. Your system just runs out of memory. And Linux has certain heuristics to look at your process, like is it run as root? Does it use lots of memory? But at some point, the killer might decide to kill you. And I would argue that stack dumps might be of limited use in the analysis here, because you actually want to find out not where you are, but why did you use up so much memory in order to be killed by the killer. So I would rather use like malloc info, heap snapshots to reason about this, write a different handler for it. And maybe it's also not your process's fault. So also write all the system information like, okay, who was using how much memory at this point in time in order to trace back the situation and find out what was wrong. The killer only sends sigkill and in rare cases sigterm to your program. That could be also you on the console. So in order to really distinguish and find out who was sending you this, you can go back to this slide where I showed you the C special, like the more versatile registration of handlers. And you can there find out, okay, it was actually the operating system and the killer who was sending me the SQL signal, and then you would be able to react specially for the killer. Okay. With this said, let's come to part 2, a serving suggestion, how I implemented this in production. I've mostly talked about development so far. Combining Google Breakpad, Sentry, and Yocto, so the Yocto system builder, to build this. And I have a bigger architecture picture for you here. On the left side, you will see Yocto project. This is where my system is built, my image is built, and my application as well is built. And they are built with recipes in Yocto. If you don't know, Yocto is just like a cooking recipe to then produce all the parts that you would need for your images, like updates and images. And for these recipes, I need to do some changes. And when I do these changes, I will explain in a second, then my app will get a special breakpad handler, or I can include then a special breakpad handler in my app. And I produce symbols every time I build an update for my embedded platform. These symbols are then uploaded to a symbol server or to Sentry directly, which then uses it from the symbol server. And via the means of normal updates, my app is distributed to my hardware. And every time I crash, I can now write a normal dump, like a stack trace dump, which is really small. I will show you. And also extra information that is maybe relevant only specific to my application. And then uploaded it to Sentry, which then mangles it all together, does the stack unwinding for me, and sends me a nice email. Hey, Christoph, something crashed in your application. And here's where it is. And this was the place where it happened. This is the version and so on. Really nice. So let's look into more of the details here. First of all, I integrated this Google Breakpad into Yocto. So this is where I changed my recipes and put more stuff in my recipes in order to have the Google Breakpad in my overall images and binaries. So here, I'm really lucky because Breakpad recipes already are included in the Meta Open Embedded layer, which you probably have in your Yocto system. So there's already those recipes existing. I just have to enable them. And these create all the cross tools which I need, which kind of do the splitting of the symbols and also give me libraries that I can integrate. And it also creates those header-only libraries, the header file to be integrated in my application. And it provides a BB class to be added to my recipe, to my application's recipe, which then can be extended to do more steps, which I can show you in a second. And in these handlers, I can also add some extras. And I will show you this now. So on top of here, you have the Breakpad BB class as it exists in the Meta Open Embedded layers. And this BB class gives you a new step when building all your software. And the step is called Breakpad Packages Preprocess, which will be executed at the right time. And what it does, it just creates a new folder and strips puts your symbols of your binary in that folder. So it uses this breakpad dump syms command to create those special symbols, which we later on will need. So what I did, my application is a bit different and needs a bit more of love to it. I registered this breakpad class in my application here. I inherited QMake, obviously. And now I say, okay, for me, I have two executables, the backend and the app itself. And because the standard recipe only accounts for one binary, I needed to add the second binary to it here in a append step. So I just appended those preprocess step, and I say, okay, please also strip the symbols of the second binary, which is the app in this case. So backend and app get be stripped. And then I use Sentry CLI, a binary tools that comes with Sentry in order to upload the symbols to the Sentry server. So they are there. So every time when a crash happens, the crash can be made more sense of because the symbols are already on the servers. So every time I do Yocto build now for updates, for example, the recipes now upload the symbols to the Sentry server, and I'm fine because I know when I have a crash, I can use the symbols, specifically the symbols I will need for them. And don't be worried. Sentry is able to find the right symbols for the right crash. That is no problem. They just need to be there. For the other libraries, I usually only build my whole SDK and take it on my host machine. And then in the Yocto SDK, you usually have those debug information split. So in user lib debug, you will find your libraries here. And these libraries are now fed libraries. They have symbols inside, like libqt5 3D quick renderer or something like that. For libqt5 core, I just checked with file whether this file actually has all the information. And yes, indeed, it is for ARM. It's not for my system. It has debug information. It is not stripped. And knowing this, I can now upload it to the Sentry server and pass some tokens and so on in order to authorize there. And voila, at the end, it said to me, okay, your ARM debug companion is now completely uploaded, which is nice. Now I have the symbols of Qt as well on my symbol server or my Sentry server. Okay, bit more information on Google Breakpad. Google Breakpad uses mini dumps, which are really small dumps. They are not the core file, core dump format. They were envisioned by Microsoft originally, and they are similar to slim cores, so to cores where you don't have the heap memory, but only the stack memories. But they are, like in my experience, way smaller, around 20 kilobytes data. So it's really nice to upload them again and to handle them, and you can always store them. They are cross-platform, so so Unix cores do not work on Windows, so Google decided, okay, we settle on Minidump because also it works on Windows. And you've seen the splitting command dump symbols before, which allows you to split the symbols individually. And you can also do that on your console if you want to do that. Minidump also comes with useful tools to do the rejoining of symbols on your console, for example. There is Minidump StackWalk, and I believe it's from Mozilla. It's able to recombine the Minidump together with your app, together with your symbols, to get a normal stack trace then after that. So you can do the same as with core files. Or to be even closer to core files, you can even convert the Minidump file to a core file, which is really nice. There's more binary inspection for that, which is not so important. Okay, now I still need to integrate the Breakpad crash handler in my code. And I told you Breakpad is a header-only library, but it's not really true. You have a static library. I'm sorry, you actually have a static library that you need to link. But no problem. Once you are using Breakpad in any of your recipes, Yocto will create the static library and put it into your SDK. It's called libbreakpadclient.a, and you need to link against it. When you do that and put 2 extra lines in main, you will see it soon. You register a Breakpad handler, and you then, of course, can do more in your custom handler than just writing a Breakpad core file or Breakpad dump, but also like write more information. Maybe where the user was, maybe the state in which your backend was. We will see in a second here. Here you see first the registration of the handler in your main. And you will see I'm just creating a Minidump descriptor, which is telling Minidump where to store the crashes, these Minidump crashes, in this case in home root crash reports. And I also register an exception handler, which I now also pass a callback, which I will talk about in a second. It's down here. But additionally, I can put more information to it. For example, a screen manager. In our case, this is telling us, okay, which screen was the user on when the crash happened? And down here, I obviously only do it in Target. I include the Breakpad crash reporter header file and can now use this callback or this signal handler, which we've already seen, to do stuff which is maybe writing extra information. In this orangey part here, I'm writing the information, the screen stack. So you were in main menu settings, audio settings when when the crash happened, or I'm then just handling the normal crash issues. Okay. Then I still need to send the information, right? And I decided for this project to let a daemon check the crash folder for crashes, for new crash files to show up. This is because I'm not really sure whether the device has connectivity when the process crashes. And this way, the daemon just tries again and again and again. And once it gets everything at once, meaning internet connection and a crash file, it will upload it. And it's not only uploading the crash file, but it's also uploading this extra information, which I just wrote in my special handler here. For now, I'm not uploading logs because I thought that they would be too big, but maybe in the future, I will just use a bit, maybe the last few lines of my logs to also integrate in this extra information to be uploaded to Sentry and to be shown there. Okay, here's what it looks like. It's also a C program. I just have two Q files, the normal file, the normal crash report, and an additional crash report. And I then just do a HTTP multipart and just a normal API call to send up the crash information from my crash daemon. Okay. And with this complete, I'm finally able to see my crash happening in Sentry, which collects all the crashes for me. And what is really nice about Sentry, it categorizes the crashes. This way, you do not get a new entry for every time the same stuff crashes all the time. You have your seg fault in that one location and you see it one time and one time and one time. No, it's actually putting together the stack traces into these categories and saying, okay, this error, for example, here in timer is enabled, is categorized in one category, which has 3 occurrences, which is really nice because I can then see, okay, is this crash happening in lots of time here? Clicking on this, we will now see all of our information. First of all, the extra information that I sent. I promised you I write this extra information like this. Oh, where was the user? And now I know, okay, when this crash happened, the user was in start menu, recipes, my recipes. Maybe something is wrong with the recipes. I don't know. And then there's the breakfast information, normal information about the Linux and so on. Maybe we should put as an extra information also the version of our software, of our app, to find out, okay, is that happening in version 5.0 or 6.0? And down here, finally, we have the stack trace, also with the top stack being the top line here. So it crashed in this line. And you can see that it actually can deduce the line numbers where it happened, something in a Q vector. Also, the symbols of libqt5 core are resolved. Additionally, there's also more of the stack down here where symbols are not available, where Sentry was able to unwind. But obviously, if it does not have symbols, it cannot tell you any humanly readable information on these addresses. And as a bonus, kind of a cherry on top, I got an email and it says, okay, there's a new alert. And here is the signal that happened. And here is a rough stack trace for your signal already. So and also the extra information, like where was the user? It is from a different one. Here, start menu, settings, my settings, something. Okay. More on Sentry. You can cluster the crashes as you want. So you can write little kind of regex-like expressions to find out, okay, what do I want to put into the same bucket? Maybe you only want to cluster for applications or for versions or something like that. Sentry actually supports more dump formats than I've shown you. I've shown you Google Breakpad. There's also Sentry native dumps, which you should check out. Maybe they're fitting better to your applications. It also supports external symbol servers, not only your own symbol servers, but sometimes you have libraries where you only have the binary files and you want to add informations from those companies that do not give you the source code, but only give you binary files. and symbols on their symbol servers, you can add those symbol servers to Sentry and then make more sense of your crash dumps. You can either run it self-hosted, Sentry, which is what we do, or you can pay a certain fee. There's different stages for it, but I think it starts at around 25 euros a month for your team to get this nice feature. And I would say it's definitely worth it. Last but not least, I'm not really a lawyer, but sending information to some clouds might ring a bell or an alert for you. And uploading crash data actually means uploading user data, right? So what we decided to do until now is to run it for development or staging and testing only. So most of the time, our users do not create those dumps, and they do not get uploaded. But we plan on doing this, and once the production is involved, we plan to make it opt-in for our users, such that they always know that they are sending this information, and you know that from other programs as well. Do you want to report on crashes happening? And again, practically, stack information might contain all kinds of information, might be really sensitive if it can be traced down to individual users. So my verdict for now is if dumps are anonymous and your users know that this telemetry is recorded, and also for what purposes, meaning only for crash analysis, the data is collected, one should be fine. Again, I am not a lawyer and I cannot really advise you legally on that, but this is just how I would do it until now. Okay, which brings me close to the end of my talk. 3 takeaways. I would say overall, there's still much one can do when it's already too late. Do not be afraid when you see your next segfault. You can still do stuff afterwards, and you can still make a reason and find out why that segfault happened, also on your embedded devices. I hope I showed you the classic ways that exist in theory, and the one way where I have this serving suggestion, which I really like in practice. Overall, invest in learning from your crash it. It really pays off. And yeah, I can only say that when we put this system on, it maybe cost me a day or 2 days or something like that, but it saved me over the time so many days on debugging and missed crashes that the users only could describe in words, that it's actually really worth it. Here are more pointers and sources if you want to reproduce what I did or like read more about the topics I presented. And with this, I would like to thank you. This is the end of my talk, and I will answer questions, all questions. Ask me anything. Thank you.
Hey, Christoph. Thank you. That was really informative. We have one question here. About how many emails would you say that you get from Sentry with crashes a day?
Yes. For our, currently we only have it deployed to our testers, as we said, our testers and developers. So it's limited until now. I would say the worst day was about 30 emails, because usually when a tester or a programmer finds out a bug, they retry it and retry it. Can I reproduce it this way? Can I reproduce it this way? All the time. And this makes it happening up ending up in many emails. But I think after a certain amount of emails, Sentry will then just send you a summary, or it will also send you a summary of a week saying, this bug you already know and categorized but couldn't fix until now happened 3 more times this week, and this new bug also happened this week. So it's actually manageable, and well, if you know email filters, you can filter it away anyways.
Nice. Just out of curiosity, what percentage of projects have you worked on bother to put the time in to implement something like this? Would you say that it's fairly popular, or are only certain industries or certain people doing this?
I've seen it in bigger projects in the automotive industry, also in the food industry. And I would say that if a project reaches a certain level of maturity, you would always find such a system. whether it be this system that I just presented or a system that is similar to it, like just uploading slim dumps or something like that. So I would say the overall majority of mature projects will have such a feature because it's really helpful.
True. So is there any other experiences with it that you could share with us? Like firsthand experiences or anything?
Yeah, well, I think again, I cannot repeat it often enough. Symbols are really big, and we now have problems of storing all the symbols that we always produce, for example, in nightly builds or with builds that happen regularly or with different versions on our servers. So you end up having really gigabytes of data being stored on servers. And I would really like to see in the future that this handling of symbols, maybe in symbol servers, maybe in ways of compressing symbols and so on, is a bit like developed further, or maybe I just didn't find it out until now. But I would really like to have a future where symbols are smaller, such that I can maybe have them on the device, or maybe have even more symbols for all old versions and all old binaries on my Sentry server or symbol servers in the cloud.
Any chance that any of these techniques work on Android?
Oh, I'm sure. I'm sure. Like Sentry is built for really many operating systems. It is running for almost all the languages you know. So I guess just check it out, find the Sentry crash handler and include it into your application. Yes, you will have crash reporting there as well.